Howdy, my name is Charles Villegas, and we are presenting the ESET 462 final project. And I'll pass it off to Peter.
Hello, my name is Peter Gottapelli.
I'm Thomas Lopez.
I'm John Ray O'Meara.
I'm Stephanie Villarreal.
And we'll get on started.
Our mission was to design a system that will balance a ping pong ball in the middle of a beam that's attached to a servo motor using a sensor at the end of the other end of the rack to determine what angle the ramp needs to be to keep the ping pong ball in the middle. This is our timeline and effort distribution divided among the five of us. Then this project was developed over a period of 6 weeks, as shown in the visualized timeline.
And for our detailed project plan, our objective was to design and 3D print the separate project components, order an infrared sensor, an Arduino, a servo motor, and some hardware components. We will then assemble the pieces, write the code, and test which variables will work effectively for the PID control. And these were the components that were mentioned earlier. We were using an Arduino Mini Nano, a Sharp IR sensor, and an S3003RC servo. This is the design for our ball and beam project. We put the IR sensor at one end of the beam, and we put the servo on the other end to allow us a separate actuating system. And this is how it looked like in reality. And moving on to the design process.
So the design process, our main goal was to maintain the ball at the center of the beam and for it to keep adjusting using a motor. So our two strategies were to try an open loop control system and a closed loop control system. So the open loop, we found that it did not receive any feedback. Therefore, make it as it didn't consider the goal if the goal was reached or maintained, while the closed loop system, it compared the actual and desired position, which was at the center. So for the PID controller, it had three different components that were crucial to minimizing the error and maintaining the ball at the center of the beam. There was the KP, which tracked the fast error response. The integral part eliminated the steady state error, and the derivative improved damping and overall stability. Um, the input for our project was the angle of the beam, and our output was constantly being compared to the ball's position and the desired position. So lastly, to derive and have this relationship with the beam and the ball, these are our calculations for both the open and the closed loop.
All right, so this is a video of the project actually working. So if you can see on the far left, we had a wallet and a duct tape kind of thing to stop um, the the beam from going too far down. Because if it went too far down, the servo motor wouldn't be able to move it back up. And so right here, this is like a screenshot from that video, and it's showing the ping pong ball staying in the center. And so we got it to stay in that position. And then if you go to the next two slides, so here's one of the edge cases of it going all the way to the end, and you saw us pushing it over. And then here's the other slide that shows it going to the other edge, and it gets, and as you saw in the video, it gets back to the center area. Next slide, passing off to John Rayo.
Sweet. All right. And in this project specifically for the special case, we decided to angle the base of the beam right around 5 degrees in order to see if the beam would still level out. And as you can see in the video, my wallet, half of it's under the beam to where it's angled downward. And that still made it to where the ball would stay in the center of the beam. This special case was useful because we wanted to see that not only, obviously, it's easy for the beam to get leveled out whenever it was flat on a surface, but having the wallet there really shook up the bottom foundation of the beam. Even with all of the external factors thrown into the system, it was still able to keep the ball in the center, proving our project was functional and everything worked properly. Thank you for listening. I hope you enjoyed it.